Okay, so while it loads, I'm Tapish. I'm an intern student from India, and I'm working on finding a distant supercluster. Now, you might think this does not look like the NEP data, and that is because it is not the NEP data. It is the DES data, but we also have Jordan here, who is working on something similar with the in the NEP field, and he's trying to find galaxy clusters. So I'll begin with why it is important to find a supercluster or a large-scale structure. Basically, what this allows us to do is it allows us to constrain the cosmology, in the sense that it allows the large matter over density allows us to put constraints on, say, sigma 8, the initial density fluctuation, etc. Also, supercluster is an interesting environment to probe things in. So I think that is why we should do this research. So yeah, we focus our research only in this region because it is the largest continuous region and doesn't have artifacts unlike others. So this is the redshift distribution. So the whole sample is in blue, while we select only galaxies, which is in orange. So as you can see, it is limited to somewhere close to 1.2. After that, it falls quite fast. So we are using photometric redshifts. So we bin our data into redshift bins. Say our redshift bin starts from z equal to 0.2 and extends to 0.4, then 0.4 to 0.6, 0.6 to 0.8. And then we have bins which are at a slight offset, say 0.25 to 0.45 and so on. This way we get a continuous coverage of all the redshifts, and this allows us to mitigate the errors due to the photo Z. We also do K correction and magnitude cuts. So we use the R band, and this is a redshift slice between 0.8 and 1. So with the magnitude cut and the redshift bin, what eventually happens is we have a volume limited sample and we avoid any sort of bias in the data, ensure completeness. So we cut it around here, minus 17.5. Just keep the brighter galaxies. So our raw data looks like this. I then generate a mask to ensure everything is neat and tidy, and there are some areas where data isn't taken, so I control those. So this is the redshift bin I'm really interested in, 1.04 to 1.24, and this is where we have found something interesting. So we generate a density contrast map. Basically, every pixel shows galaxy counts, and they are scaled by the mean galaxy counts in the whole field. So yeah, right now it isn't much. So what we do next is create a smooth density contrast map. Basically, we use a 2D Gaussian kernel and smooth everything out. So what that does is it allows us to look at over densities over multiple pixels because they're smoothed out over in the 2D space. So over here you can see there's some structure over here, high over densities in these 2 points. So obviously we can make a contour plot, and you can see there's like a 4 sigma over density. Okay, so this, you can see the redshift evolution of the structure. I'll play this again. So you can see things are popping up and going out of scope. I'm not sure if you noticed, but there was another structure at a lower redshift right in this space, which we'll come to later.
Can you put it again?
Yeah, fair enough. So, over here, this thing, yeah, it disappears and comes back. So that was at around redshift 0.7. This is at around 1.1. So, yes, this is the question. Where is it located? So, these are the count ratios in the region of the supercluster, which is in orange, versus the whole field. So, you can see the supercluster region suddenly increases around this redshift versus the field. And this corresponds to this peak, which is our supercluster. The other object I noted a moment ago is another object in the line of sight. And we think it is a smaller cluster which is in the same area in space. So we generated a radial profile for our supercluster. And as you can see, it is quite interesting that there is like a break at 120, 150. Quite steep. Also, so defining the radius for the supercluster isn't so trivial because we don't know where to keep the boundary. So one way is we can check the significance versus the size of the cluster. This is the diameter in R8 tech space, in megaparsec scale basically. So as you can see, we have a 3.5 sigma at 40. So 3 sigma detection is around 80 megaparsec in size. So we are quite confident of the existence of the structure. And again, it sort of flattens out around the diameter of 160 or the radius of 80 megaparsec. So in the end, I basically would like to present this new supercluster to you, which is at redshift 1.1, size of similar to 100 megaparsec, and is one of the farthest structures of this size ever found. So, yes, and we are hoping to employ this technique and find more galaxy clusters in the Akari data as well. Thank you.
Any question?
Yes, please.
I'm wondering the next slide. How do you calculate? You measure that. Yes, this one. You measure that there are sigmas. They are significant of this. But I'm wondering how do you count the distance?
So what we do is this size is in megaparsec. So we take this sort of map, not this map, yeah, say this map, and we generate, say, corresponding to the size of 20 megaparsec, we'll have a circle of diameter 20 megaparsec, and we'll place it randomly over all the field, and then we look at how overdense our structure is compared to the rest of the field. So that is how we make it. So we can increase the size of our circle. So say it becomes bigger. This is 100 megaparsec. So we are looking at bigger circles all over the field, and we look at how overdense it is comparatively.
Maybe my question. Yeah, okay, I know. And but what model do you take to measure the distance? Because the distance always be problems to measure such far away. How do you measure the distance, physical distance? Because this angular distance.
Oh, okay.
How to transfer to? Yes.
So, yeah, this looks like angular distance, but this map is already scaled, so such that 1 pixel is 4 megaparsec cross 4 megaparsec. Yeah, you can't tell but it's actually stretched like this.
Okay, thank you.
Any more question? So, I think there is no more question. So all the official talk is over now. So now Professor Hyung-Mok Lee, the director of Kashi, is going to give us a summary about this conference. But before doing that, I think Tomo, do you have anything to say?